So today we will be talking about Turing machines. So in the previous lectures, we talked about DFAs and NFAs for recognizing regular languages, and we talked about non-deterministic push-down automata for recognizing context-free languages. Now, today we will introduce an even more powerful machine that recognizes a larger set of languages. In fact, as we will see later, the Turing machine can do anything that a general purpose computer can do. So as we will see, a Turing machine can be a theoretical model for a general purpose computer. It can do anything that a computer can do. Or, in fact, it's used as a formal definition of an algorithm. So an algorithm is a well-defined sequence of steps for solving a problem. So anything that you can solve using computers, you can do that with an algorithm. Right? Any solution any program that you write, this program implements an algorithm. And that algorithm is just a sequence of steps for solving a problem. And as we will see later, not all problems are solvable using algorithms. Not all problems are solvable using computers. So we think of computers as amazing machines that can do anything. In fact, they cannot do anything. So there are things that computers cannot do. There are problems that computers cannot solve. There are problems for which there are no algorithms. And we will see this, we'll understand this concept better when we look into examples. Now let me just give a high-level description of a Turing machine and how it differs from finite automata and push-down automata, or how it's a more powerful machine. So clearly, in order for this Turing machine to recognize a larger set of languages, it has to be more powerful. And in order to be more powerful, it has to have more features that we don't have in finite automata and push-down automata. Now let me ask a question. What's that feature that push-down automata has, but finite automata don't, that allowed us to recognize a larger set of languages? What's the feature that? What's that? The stack, yeah. So a push-down automaton is more powerful than a finite automaton because it has a stack. And that stack allows a push-down automaton to remember things. It's memory. It's some kind of memory. Now, a Turing machine has memory, but it has a more general kind of memory. It has an unbounded tape. It has an unbounded tape on which it has the input. So the input can be A, B, B, C, A. So this is an input string. And then on a Turing machine, there will always be a certain symbol to mark the end of the input, so that the Turing machine knows where the string ends, because this memory that's available to a Turing machine. And the Turing machine is a theoretical model, by the way. So we're talking about a theoretical model. So this Turing machine is just a theoretical model for a general purpose computer. So this is infinite. But this Turing machine will have its head, the head of the machine, on this first symbol in the input string. And there is some kind of another symbol like the blank to indicate or to mark the end of the string. And clearly, this symbol cannot belong to the input alphabet, right? So it must be a distinct symbol that does not belong to the input alphabet. So this is the actual string. The string has symbols that belong to the input alphabet that we call sigma. And in the Turing machine, there is the tape alphabet that we call gamma. So sigma is the input alphabet, and this blank symbol does not belong to sigma, and gamma is the tape alphabet, and this symbol that marks the end of the string belongs to gamma, and sigma must be a subset of gamma. Sigma is a subset of gamma. Now, so far we have introduced a feature that the Turing machine has, but finite automata and push-down automata didn't have, which is this unbounded memory. Now, the power of the Turing machine is not limited only to having this unbounded memory. The power of the Turing machine that distinguishes a Turing machine from the less powerful automata is that it can read and write. So it doesn't only read from the input, it can also write. So it can choose to replace this B with a C, for example. So a Turing machine not only reads from the input, it can read and write. And this head of the Turing machine can go left and right. So this head can go right, and it can also go back to the left. So if the tape of the Turing machine, if the head of the Turing machine can go left and right, this means that a symbol in the input can be processed multiple times. And the fact that you can process a symbol multiple times makes the Turing machine more powerful, but also makes it more complicated, because now a Turing machine is not guaranteed to terminate within finite time. Finite automata and push-down automata are guaranteed to terminate within finite time because the input string is finite, and each symbol in the input string is processed only once, is touched once. So finite automaton or a push-down automaton touches a symbol in the input string only once, and the input string is finite. Therefore, a finite automaton or a push-down automaton are guaranteed to terminate within finite time. Now, in a Turing machine, the Turing machine can process or can touch each symbol multiple times, an unlimited number of times, which means that a Turing machine may not terminate within finite time. So the Turing machine, the extra features in the Turing machine has an unbounded tape or memory, which is memory. It can read and write, and it can go left or right. Which implies that an input symbol in fact, when it goes left and right, it doesn't have to process an input symbol. So it can go beyond the input string. So this is, in this example, we have an input string with 5 symbols in it. The Turing machine can go beyond that, can write its own symbols beyond the input symbol. So, just like a computer program that we are familiar with. Your computer program reads a certain input. There is an input to your program, but your program also writes, and it also it can generate all kinds of data structures in memory. So that's what you have in memory at any given point can greatly exceed what you have at the input. What a program writes in memory can be much more than what the input is. So this is we are going now to a much more general model of computation. So an input symbol may be processed multiple times. So a Turing machine is not guaranteed to terminate. So just like a general program, a program written using a general purpose programming language may not terminate. It may have infinite loops. It may have infinite recursion. It may have recursion without a base, and then it will never terminate. So termination is not guaranteed. Not every algorithm is guaranteed to terminate. Now this introduces the concept of decidability versus recognizability. So a Turing machine, because the Turing machine can have, given an input string, in a Turing machine now you can have 3 possible outcomes. 3 possible outcomes. One is accept, one is reject, and the third one is loop forever. Loop forever, or infinite loop. Now this outcome was not possible in finite automata and push-down automata. In a finite automaton or a push-down automaton, you either accept or reject. You are guaranteed to terminate within finite time. And this loop forever is not there. Because by definition, when we describe the input, it's you always make you have to process the input string, and with an input string, it's you have to process the symbols of the input string, and if you end up in an accept state, that's an accept. If you end up in a reject state, then you reject. So now we have the notion of decidability versus recognizability. So if a Turing machine ends with an accept or reject, we say that the Turing machine has decided the input string. So if the outcome is accept or reject, we say that this input string has been decided. Or in other words, if for a given language you can find a Turing machine that will either accept or reject and is guaranteed not to loop forever, then you say that this Turing machine decides this language. So if if given a language L and a string S, if there is a Turing machine that that either accepts or rejects, that either accepts or rejects this string, the given string in finite time, we say that the Turing machine decides L, or L is Turing decidable. L is Turing decidable. So a language is Turing decidable if you can find a Turing machine that will either accept or reject. Now, if we change this definition, given a language L and a string S, if there is a Turing machine that that accepts S if S belongs to the language, and either rejects or loops if S does not belong to the language, we say that the Turing machine recognizes L. And L is Turing recognizable. Okay, so do you see the difference between decidability and recognizability? So if you can find a Turing machine that will either accept or reject within finite time, it accepts every string that belongs to the language in finite time and rejects every string that belongs to the language in finite time, we say that the Turing machine decides the language. If we don't have a machine that decides the language, we have a machine that if the string belongs to the language, it's going to say, it's going to accept it. But if the string does not belong to the language, the machine will either reject it or loop forever. So if the string does not belong to the language, the machine is not guaranteed to terminate within finite time. In this case, we say that the Turing machine recognizes that language. Now, given this description, which set is larger, the set of Turing decidable languages or the set of Turing recognizable languages? Which one will be larger? Recognizable. Yeah, exactly. Because recognizing is easier than deciding, right? So if a language is decidable, it's recognizable. Because here, recognizability, it's if the string belongs, it accepts it. If it does not belong, it either rejects or loops. So it doesn't have to loop. Right. So if a language is decidable, every decidable language is recognizable, but the opposite is not true. course, we will show, this lecture and in next lectures we'll show examples of decidable and recognizable languages, and with the examples you will fully understand the concept. So now let me, after introducing this, let me draw the hierarchy now of languages. So we have the smallest set that we started with, which is regular languages. These are the languages that can be recognized using a finite automaton. And then we introduced the set of context-free languages, the set of languages that are recognized by, that can be recognized using non-deterministic push-down automata. And now we have a larger set of languages, which is the set of Turing decidable. The Turing machine is more powerful, and it can decide a larger set of languages, Turing decidable. Now we know that, it's just, if a language is free, it's clearly decidable. Why? Because a Turing machine is more general than a push-down automaton. And a Turing machine is more general than a finite automaton. So a Turing machine can easily simulate a push-down automaton, and it can easily simulate a finite automaton. It's just, when it simulates something that is less powerful, basically it's using fewer features. So it has more features. The Turing machine is more general. It has more features. So when it simulates something that is less powerful, it just uses a subset of the features that it has. Okay, so it's easy for the more powerful machine to simulate the less powerful machine. So that's why the set of regular languages is and context-free languages is a subset of the set of Turing decidable languages, and the set of Turing decidable languages is a subset of what? Turing recognizable. Okay, so there are other names, equivalent names for, or alternative names for these. So Turing decidable languages are called enumerative languages. It's called recursive languages, and this is the set of recognizable languages is called recursively enumerable languages. So this is recursive, and this is recursively enumerable. So these are alternative names for Turing decidable languages are also called recursive languages, and Turing recognizable are also called recursively enumerable languages. Okay, so now let's give a high-level description of a Turing machine that will recognize, or that will decide, in fact, one of the languages that we have studied and shown to be non-context free. So let's give a high-level description. By the way, a state diagram for a Turing machine is going to be messy, and we will only see an example of only one small example for one language, for the state diagram for a Turing machine, because it's messy. But in most of the time, we will give a higher level description of a Turing machine, not a complete state diagram. For this case, so let's look at this example. L is W pound W such that W belongs to sigma star, and sigma star is, let's say, 0, 1. Sorry, sigma is 0, 1, and W belongs to sigma star. So this is W separator, some kind of separator W. Now, this is a language that that is not regular, and it's not even context-free. So last time we showed a language that that is similar to this, looks similar, that is context-free. And what was that? Yeah, the palindrome. So WWR is context-free, but WW is not context-free. You know, it's easy to write a grammar for this, but if you try to write a context-free grammar for this, you will not. You will not be able to write a context-free grammar. Because if you think about it, for the palindrome, we wrote this grammar, A S A or B S B or epsilon, and this guarantees that you have this kind of symmetry around a certain axis. So for this we could write a context-free grammar, but try to write a context-free grammar for this, you will not find a way. So you cannot say something like this. S is, for example, S1 or AA, for example. An attempt would be S is AA, and then A is anything, or BA or epsilon. Will this generate this? No, it will not generate this. Why? Because what you use for there is nothing that will force this A to be the same as this A. So this is an arbitrary string, and this is an arbitrary string, and these two A's can be different, right? So this is just a naive attempt to construct a context-free grammar for this. But there is no such grammar because this language is not context-free. Okay. So now how does let's show by example how a Turing machine can recognize this language. So let's look at this example. One, zero, one, one, 0, 1. Okay, so this is the input string, and this is the Turing machine. So this is the head of the Turing machine. Now the Turing machine can go left, the head can go left and right, and it can also write. So the algorithm for recognizing this is checking if the first symbol matches the first symbol after the pound, and the second matches the second after the pound. So you can do this in a systematic manner by using crossing. So you can say, okay, at this symbol I'm going to cross or mark this one. I'm going to mark it. Mark this, to indicate that I'm done with it. And then compare, the symbol that I have just read. Then the head goes right until it finds the pound sign, or the symbol that indicates, that separates the two parts of this string. And then it it checks the first symbol after this. Is this equal to the symbol that we have crossed? If it's equal, then we're still then the test passes, and the string so far satisfies the property of the language. So it's going to do this. It's going to mark this. And then now we have marked this and this after matching them. And in fact, the Turing machine can keep doing this. So now, if the head is here, now the head will go left. So it will keep going left and checking until it finds what? Until it finds? No, it doesn't know. It will not stop here because it will not know that this is the first unmarked symbols. It has to go all the way to the X to find the last marked symbol. So it will have to go all the way to the left, one step at a time. So each one is going to be a transition. So that's why our description of the Turing machine here is high level, and we are not showing all the details. So the head will get to this X one step at a time. So each time it will go one step to the left, and it will check, is this an X? No, it's not an X. Go to the next. Is this an X? No, it's not an X. Go to the next. Is this an X? No. Is this an X? Yes. So it will keep going and checking if it's an X or not. Now it's an X. When it finds an X, what should it do? It should go right. If it finds an X, it should go right. And now this is our next symbol to check. And it's a 0. So it's going to mark it. Now each line here that I'm drawing does not represent one step. It has multiple steps in it, as we have seen. So this is an X. So it's going to mark this. And then it will go to the 1 pound X01. Now we are here. Now what should we do? So this tape should go right until it finds a what? 0. No, it doesn't know if it's looking for a 0 or a 1. Yeah, it needs to go for the X. So it should go one step at a time until it finds an X. Then it checks. So then it goes to this 0. So whatever the symbol after the X is gets compared with the last marked symbol. So this should match this. And if it matches, then it's going to mark it with an X. So clearly this is tedious, but it works. So this is X1. And then it's going to do the same. So we are here. It's going to keep going left. So this head will go left one step at a time until it finds an X. Then it looks at the symbol. Then it goes right. So it keeps going left until it hits an X. Then it goes right. What comes after the X is this. It says, OK, now this is the next symbol to match. And it marks it with an X and goes right. And again, I'm skipping many steps. And now it's here. The tape is here. Then it goes left. Then it goes right, until it finds the last X, right? So what we should be looking for now is the last X. So X, X, X. The first symbol that is not an X should get matched with the last symbol that we marked here. So this should be a 1. And by the way, this is this is similar to a program that you would write to do this, right? You can easily write a program that takes this as input and determines if the two strings on the two sides of this this special symbol, if they are equal or not. So basically, you write a program that does this. It's going to loop. It will check this, and it will then it will compare it with the corresponding symbol to the right of the separator. And now it's going to mark this as an X. And we know that the string belongs to the language if what? If we are, if we mark everything, if everything is marked, so you do a scan. If everything is marked, then the string belongs to the language. If it's not, if there is something unmarked, then the string does not belong to the language. Or if any matching fails, like here, if we had if we had a 0 here. If we had a 0 here, then the first matching would fail, and then the Turing machine would go to a reject state. So this is a problem that is Turing decidable. It's a problem that can be decided by a Turing machine, or in fact it's a string that can be decided by, it's a language that can be decided by a Turing machine. So yeah, so this looks like, this may look primitive. In fact, yeah, you can think of the Turing machine as a primitive model for a general purpose computer, but it can do everything. It can do anything that a general purpose computer can do. It may take more steps, but you can do with it anything that a general purpose computer can do. Now let's look more closely into the transition function for a Turing machine. Oh, I needed those. So the transition function a transition function for a Turing machine, delta, is going to take a state and a symbol, and it's going to go to a state, another symbol, and a left or right. Okay, so for a small example, suppose that we have this Turing machine. This is A, B, B. And we are in state Q0. And we have the tape here. And we have delta of Q0 and B equals, say, Q5 and C, or let's put it, let's not put it here. Let's put it, let's say, delta of Q0 and B equals Q5, C, and right. So the transition for a Turing machine should specify, let's make it Q4, so that don't confuse it with an S. So the transition for a Turing machine specifies the next state, what to change the current symbol in the input to, and whether to go left or right. So this is, this is what? This is the current state. This is the current symbol in the input. Current symbol in the input. What's the definition of current symbol in the input? What the head is pointing at, where the head is. Where the head is. And this Q4 is going to be next state. What's this C? This is what to replace the current symbol with. What to replace the current symbol with. And what's the R? Go right. Direction. Yeah, that's good. Direction.
Can you move him right after you've replaced the symbol or before?
Yeah, we will show it right now exactly what will happen. So what will happen here, we will get this. So this B becomes a C. So we replace, then we move to the right. So this shows us a single transition in a Turing machine. And as I said, when we solve non-trivial problems, we will not be able to show this level of details for the Turing machine. So if we are here and we apply this delta of Q0 and B is Q4, replace the B with a C, replace a B with a C. So it basically says change the state to Q4. Your state becomes Q4. Your B becomes a C. And move the head to the right. So if this had been an L, we would have put the head here. Right? If this thing had been an L instead of an R, we would have moved the head to the left, and we would have put the head here. Okay? So this is how it works. So let's now give the formal description of a Turing machine. Of a Turing machine. So a Turing machine is, so the finite automaton was a 5-tuple, the push-down automaton was a 6-tuple, and the Turing machine is a 7-tuple. Is a 7-tuple, and it will have Q, sigma, gamma, delta, Q sub S, Q accept, and Q reject. Now, so we are familiar with everything, in fact. So Q is a set of states. Sigma is what? The input alphabet. And gamma is the tape alphabet. So in push-down automata, we have the input alphabet and we have the stack alphabet. And we have the end does not belong to sigma, and it belongs to gamma. And delta is the transition function. So the transition function in a Turing machine, it takes a state and a symbol in the tape alphabet, and it gives you a state. It gives you a state, and what's this? A symbol in the gamma alphabet, and a left or a right. So this is what the transition function in a Turing machine is. So it takes a state and a symbol from the tape alphabet, which is the bigger alphabet. The tape alphabet is a superset of the input alphabet. So it takes a state and a symbol, and it gives you a state. What's the next state? What should the symbol, the input symbol, be replaced with? And go left or right. And QS is the start state. Q accept is the accept state. and QReject is the reject state. Now we have to have an explicit reject state. We have to have an explicit reject state because that finite automaton may not terminate within finite time. For the finite for finite automata and push down automata, we know that we are done when we finish processing the string. We know that we are done. When the string is completely processed, we know that we are done. But in the Turing machine, we need a reject state because we need to know when to stop, because we can process the string multiple times. So processing the string cannot be the termination condition in a Turing machine, because you may process it multiple times. So you need an explicit reject state. Now, having one accept state does not, by having one accept state, we do not lose generality, because as we have seen in NFAs, even if you have multiple accept states, you can always have an epsilon transition. You can unify them into one accept state, and then these are no longer accept states. So if you are given an NFA with multiple accept states, you can always convert it into an NFA with one accept state. And so having or requiring an NFA to have a single accept state does not make it less general. Okay? So this is the formal description of a Turing machine.